Ya se va a oír. Espero que estén todos bien. Y me queda la duda si han estado recibiendo bien el link donde nos hace favor el doctor de cargar la presentación. Sí la han estado recibiendo todos bien, porque sí hay quejas de algunos que dicen que no lo han podido abrir. Y ya ven que les envié el link y hay una clave, un password que tienen que ponerle. Yo lo he abierto sin ningún problema. ¿Alguien no lo ha podido abrir? ¿Sí? Bueno, no lo han checado. Bueno, por favor. Y luego el de ayer era con el mismo password. Bueno, chéquenle por favor y nos avisan, porque yo sí los abro muy bien, pero no sé quién comentó que no lo pudo abrir, pero no me lo dijo a mí. Entonces, bueno, por favor, chéquenle y nos avisan. Mañana comenzamos a las 2, por favor, y les vamos a estar avisando diario si podemos lograr que todos los días que restan sea aquí. Pero por favor pongan atención en los mails y en los comunicados que les enviamos. Bueno, muchas gracias. Entonces, de una vez empezamos, le damos otra vez la bienvenida al doctor Cristian y pues arrancamos. Thank you.
Thank you. Okay, welcome everyone to our lecture today. Actually, we almost finished yesterday. We just had 2 slides left, so we will finish these 2 slides and then we will move to the next topic. I already provided this file to you, so you should have it by now. So it's basically a summary which is missing. So we ended with the classification of microbiomes into aerobic and anaerobic microbiomes, and also this intermediate with microaerophilic microbiomes. So we also discussed already which advantages the application of microbiomes has. You gave some good answers, and here's just a short summary of this. I searched for some sources which are supporting this information. For example, microbiomes allow a rapid conservation of almost all organic compounds because we have a high metabolic diversity. We have a really high redundancy and high adaptability. That's also what we discussed. We have a rapid growth. So there are many microorganisms which can grow relatively fast, and after a short while you will reach already a high cell density. And lastly, there's a high robustness. So it's really difficult to change the microbiome in order to change its functionality. So it's really hard to disturb the process. Usually you can throw everything into a biogas plant and then the microbes are doing the job, and in the end you're getting a lot of methane. So with this, the last chapter is, or chapter from yesterday is done, and we can shortly summarize it. So we talked about oxygen and the possibility to separate different microbiomes based on oxygen. We also talked about the possibility to use oxygen to fasten up microbiomes, which was really important for the wastewater treatment, but this does not allow the accumulation of really valuable metabolites that we could use to sell to the industry. This is then possible with anaerobic conditions, where we have very low redox potential, and oxygen is not the final acceptor for the electrons, and therefore we have not a complete degradation of most of the substances that we have present, and thereby we are producing methane or other substances of interest. Although this is nice, it's really difficult to enrich microorganisms under anaerobic conditions. So they are washed out easily because they are growing slower than with oxygen. And to circumvent this problem, we can apply some growth bodies, or we can use these UASB reactors where we have some selection pressures that support the formulation of granules. We can also use membranes, a membrane reactor, to somehow retain the biomass in the reactor. So that's it. So we are done with this, and now we can already move to the next presentation. So can you please change the, yeah, thank you. Okay, thank you. Then let's start with our lesson for today. So today we talk a little bit more about engineering. So we are leaving for a moment the biological perspective, and we will talk more about anaerobic digestion, how it's working in general, and we will also talk a little bit about dark fermentation. So what is anaerobic digestion? What do you understand under anaerobic digestion? Yes? Yes? And how does an anaerobic digester look like? Mm-hmm. Yes. But can you imagine a reactor how the reactor would look like? How would we perform anaerobic digestion? How would we start the whole process? You don't know? Anyone else has an idea? Yes, please.
Well, actually, I've seen anaerobic reactors. We went to a water sewage treatment plant,
Yes.
and they produce an anaerobic reactors to create energy.
Yes.
Well, they kind of look like they're closed. They don't have any contact. Well, they try to minimize the contact with the oxygen. They were massive. They were really big. And I don't know. They look like they were cylindrical, and they have a bulb above, so the gas has a place to go, I guess.
Mm-hmm.
And I don't know how else to describe them.
Okay, that's already something.
Okay.
Any other ideas, or has anyone else seen an anaerobic digester which looked maybe differently? Yes, you?
In my master project,
Yeah.
I'm working with the anaerobic digestion, but
Yes.
not with the biogas.
Yeah.
I'm using the digestate, the subproduct of the anaerobic digestion. But there are many differences between many reactors because not are the same in every process. There are different kind of reactors. Maybe, sometimes it's like a cylinder. Sometimes it's like for example, in Boston,
Yeah.
it's like a head. And here in Mexico, it's like a cylinder, but in the Chinampa that I'm working, it's a bag or something like a bag, a human
Yeah,
member. No?
that's
Something
right.
like that.
This also
Yeah.
exists. Yeah. Okay, you have already more or less an imagination how anaerobic digesters look like. We will go a bit more in detail for this. And then, what's dark fermentation? Do you know about dark fermentation? What's the difference between dark fermentation and anaerobic digestion? What do you think? No ideas? You look like you want to say something? No?
It's your question is about the dark fermentation.
Yes, what's the difference
okay.
between anaerobic digestion and dark fermentation?
Okay, the dark fermentation is for produce hydrogen,
Yeah?
and the anaerobic digestion is for produce biogas. Means for the methane.
Okay.
Methanes.
Do you remember why is that so? What's happening or what's done differently in an anaerobic digester compared to a dark fermentation system?
I'm not remember that.
Okay. Anyone else knows? Yes?
Well, our guess was that like the type of microorganisms that are in the reactor, like
Yeah.
that we have for fermentation. We will have what? Fungi or bacteria, or the different type of bacteria.
Yeah.
And in the anaerobic digestion, I don't know, the microbiome is going to be different.
Mm-hmm.
I'm guessing the conditions are pretty similar because both of them occur without light.
Yeah.
I don't.
But how can you change the process that suddenly no methane is produced anymore, and that we suddenly start to produce hydrogen?
Also, I guess also what they're consuming, what they're using, their food, their meal, the nutrients that they have.
Well, they could use the same. Now we have 2 reactors. Each of them receives a certain substrate. And then we have to do something differently in the dark fermenter in order to not produce methane. Yeah, you know it? But you have a guess.
Maybe dark fermentation is inside of the anaerobic digestion, is part of the process.
Yes, that's right.
But I know that the fermentation is first.
Yeah, that's also right.
The complete process is the anaerobic digestion, no?
Yeah, that's also right.
But I don't know more.
Okay, great. So that's already something. So we know now that we have several phases of anaerobic digestion, and some of them are regarded to the dark fermentation. And now we have to stop at some point methanogenesis. That's now the tricky part. I don't know whether you have some ideas how to approach this. Otherwise, I will not resolve it yet, because we will explain it very much in detail in the coming slides. So any creative ideas that you want to share? Okay, then we will just get started, and you will see step by step how this is working. So where are we now? We are now in chapter 4, so we basically covered 50% of the whole module. I think we are good in time. And the topics for today are the basics of biogas production. Then we will also learn how biogas production actually works. In this regard, we also want to discuss different reactor systems that we apply. Several of them are actually applied industrially, at least in Germany. And some of them are maybe have been applied, but not really are used anymore. And then in the last part, we will resolve the question that I just asked, how to change an anaerobic digester in order to produce something else, something value added, which is much more valuable than methane, which brings us to the dark fermentation. Okay, let's start. So we talked about this classification based on oxygen. So we start with any kind of waste that we want to turn into something valuable. And we decided that we split it into aerobic and anaerobic systems. So which kind of systems do we know for aerobic and anaerobic systems? Which methodologies do you know to treat the waste? Some of them we just mentioned.
Aerobic is like a compost.
Yes, that's right. And anaerobic.
Anaerobic waste fill. No, landfill.
Oh yeah, we can also name landfill.
Like
yeah, it's also kind of anaerobic digestion, but also it's a system that we can apply. That's right. Okay, then we have these systems here, composting, and here I differentiated between fermentation and co-fermentation. So very often we are applying co-fermentation in the field of biogas production, but sometimes we also have fermentation where we have just one single substrate. This is, for example, the case in wastewater treatment, where we have just this sludge that we are receiving from the waste activation or sludge wastewater activation. and then the sludge is brought into a digester, and there we are producing biogas. We could also think about having a bioreactor filled with manure, and then we are feeding it with a certain substrate. And if we just use one single substrate, this could also be a fermentation and not a co-fermentation. Co-fermentation has some advantages, which we will discuss later on in detail as well. And we will start with this nice picture, which shows biogas in a picture. So here you see possible feedstocks that we can use. So we can use bio-waste, residues from animals, waste from agriculture, or the sewage from the wastewater treatment. And this goes now in this vessel, in this really big vessel that you mentioned already, where actually nothing is inside. Usually a stirrer is still inside, but that's basically all. So it's a really simple system that you fill with an active medium. Very often in Germany we just use cow manure, which contains all the microorganisms that we need to produce biogas. And once the whole thing is filled with cow manure, then we can feed it. We can take some waste, solid waste, which is biological, and then we feed it into the biogas plant, and then all the microbes are eating it and converting it into biogas. So the biogas is here, it's collected, as you already mentioned, and then we can incinerate it in a CHP plant in order to produce electricity and heat. We also have the digestate, that's what you are working with, as I understand. Kind of? Yes, that's the digestate. That's what comes out here. So once you're done with the fermentation, you have some residues which don't yield so much biogas anymore. You take it and then you can still do something with it. And I assume that's what you investigate to find the right application to do something useful with this digestate, right? Yeah, so there are different things that you can do. Here, for example, they suggest a solid liquid separation, and then the liquids could be applied as fertilizer for agriculture. You could grow some fungi with it, or you could use it to grow some insects. Yeah, I don't know what this is. Anyone recognizes this? It's not very clear. Maybe this is a compost? Yeah. Then here are some characteristics, what's happening in the sludge. So the buffering capacity is going up. Antibiotic resistance genes go down. This is nice because we don't want to spread antibiotics, as we discussed yesterday. Pathogens are also going down. And here's a mistake. Anyone sees this mistake? Anyone concerned about this bubble here? Yeah, in this bubble is a mistake. You can't read it because some are so... It's not clear. So, okay, here it says volatile fatty acids go down and free ammonia nitrogen goes down. Do you think there's a mistake? Yeah, that's right. Yes, that's right. That's right. So the ammonia usually accumulates. Under anaerobic conditions, we can't really degrade ammonia. Only the volatile fatty acids are going down because they are degraded. They are the substrate for our microorganisms. Okay, now we know how a biogas plant works, more or less, in a simplified way. And now we want to collect the biogas. But what's actually inside the biogas? What is the composition of biogas? Which gas fractions would you expect? Methane, yeah, that's right. Anything else? Yes, carbon dioxide. Anything else? Just carbon dioxide and methane?
Sulfide acid, hydrogen sulfide.
Yeah, hydrogen sulfide is right. Anything else? So now we have methane, carbon dioxide, hydrogen sulfide. That's all. That's all? Yeah, so basically you're right. I mean, the main components are methane and carbon dioxide. But then, similar to the hydrogen sulfide, we have several trace elements that we still find in the biogas. For example, a little bit of water, which is contained in the gas, or nitrogen. I mean, usually no nitrogen is produced, but sometimes you might have a little bit of nitrate and nitrate, which can then be further oxidized to produce nitrogen. Sometimes there is a little bit of residual oxygen, and also a very tiny amount of hydrogen could be in the biogas. Yeah, you see that the amounts, the concentrations are extremely small. And then the main components are really methane and carbon dioxide. So what's the ecological impact of biogas? So we know that carbon dioxide is a greenhouse gas. We know that methane is a greenhouse gas. I don't know whether you know that hydrogen sulfide has a really bad smell. Pardon? Like rotten eggs, that's right. So if you can smell it, then everything is okay. But if the concentration goes up, then at some point you stop smelling it, and that's the point where you should go out of the room, because then you could actually die. And there are already accidents that happened when people had rotten meat in closed rooms, and then hydrogen sulfide can be produced. So if you go in a closed room and you see someone laying next to the rotten meat, just run and don't try to help him, otherwise you will lay next to him. So we have nitric gases. They are also greenhouse gases. Some further gases in parts per million, silicon dust. So all this is not really nice for the atmosphere, of course. So it's nice if we collect the biogas, then we incinerate it, then we have something out of it, and it does not directly enter into the atmosphere. What is actually meant with the GWP, the global warming potential? What does this mean? Have you heard about this term before? Shaking your head? No? Okay, so the idea is that, that there are some gases which are worse than carbon dioxide. And usually we are talking about carbon dioxide that we want to get out of the atmosphere. But then there are some gases which are much worse than carbon dioxide, as for example the methane. So if you don't know the term, I will not ask the question whether it's a lot, because then I have to explain the term first. So the global warming potential describes a relation of other gases to carbon dioxide. For example, methane has 25 until 68 times the global warming potential of carbon dioxide. So it's 28 times worse than carbon dioxide. Of course, we don't want, therefore, the methane in our atmosphere. So it's much nicer if we collect it, then we incinerate it. By this, we get some energy. And after incineration, it's just CO2, which is then less dangerous for the atmosphere than the methane. There are some gases which are much, much more worse. That's why I was asking, is this a lot? For example, there are chlorofluorocarbons, and they reach a value up to 11,000. So they are 11,000 times as bad as carbon dioxide. And of course, these gases should be forbidden. I don't know whether this is always in every country the case, but at least in Germany, it's not allowed to use such gases for industrial processes anymore, or at least it should be reduced to a minimum. So here's a little task for you. I found this really nice scheme or diagram in this article. And I wonder whether you can see what this diagram is telling us. Maybe we can start by explaining what we are seeing in the axis. This is the energy which is produced by the respective biogas plant. So here we have small biogas plants, and here we have big biogas plants. And here we have a value which shows us how much tons of carbon dioxide are released if we combine all underlying processes per megawatt hour of energy that is produced here. This means each bar shows us some emissions and some savings in carbon dioxide per megawatt hour. So is there something strange in this diagram? Is there something that you don't understand, or it somehow seems odd to you? No? For you, everything looks fine? Why?
It's a like comparison between energy crops and requirements of energy. I don't understand totally understand that.
So, okay, so you mean it's clear that there are some emissions, but also some savings due to the incineration of the gas. So this seems clear to you. But apart from this, is there something which is somehow strange? Is there something that you don't like, or somehow is strange?
Well, I think it's it's kind of weird that the small production of energy is more sustainable than large production.
That's right. That's really strange, right? So why is that? I mean, is here the solution that we are just building smaller biogas plants to make biogas more sustainable?
Maybe it's for cycle of life.
Yeah. So I don't know whether they did this based on a life cycle assessment. I don't know how they calculated this exactly. I would have to read the article again. But we could assume that with life cycle assessment, you could make a graph like this. So with this, you could estimate the production of CO2 and the savings. So we could use such a method to apply this, to show this. But assuming that this is all true, what we are seeing here in this diagram, and I would believe it's true, but still it's strange that the small plants are so sustainable. So why are these small plants so sustainable? No idea? Anyone else has an idea?
Venturing, I guess. Well, I'm guessing reading from the graph, using the information from the graph, it
Yes.
says that the most CO2 that we save is from substituting thermal energy and substituting mineral fertilizer. I'm guessing for larger plants, there's not enough production of energy or fertilizer for it to fully fully substitute the process, like fully substitute the amounts that need to be used. So that is why you don't have as much savings.
There's another reason.
That's yeah.
I mean, it's true that the substituted mineral fertilizer is relatively high. But there's another reason. Okay, then I will just resolve it. So it all is explained with these bars here. And yeah, maybe it's a bit small to read, so maybe that's the reason that you didn't find the answer. So this is the farm manure. And usually in small biogas plants, those are plants in relation to agriculture, where the farmers try to get rid from their farm manure and to do something useful with it. And especially the farm manure has a really bad carbon balance. So if you just leave it outside on the fields, then there's a lot of methane going into the atmosphere. And you're saving all this in the moment when you put your farm manure in the biogas plant. And in the larger biogas plants, they are more industrially, let's say, so they are filled once with farm manure, and then they rather feed certain substrates to them, like bio-waste or any kind of residues that are collected. So therefore, the ratio between farm manure and other substrates is very different. And well, especially the farm manure releases a lot of methane and carbon dioxide in the atmosphere, which we can save when we throw it into a biogas plant. In general, it's quite surprising how low the gain is. So it's almost close to, yeah, here 0.36. I think the numbers are relatively small, and here, especially with a large plant, it's close to zero. So it means you're not releasing so much CO2 in the atmosphere, but you're not saving so much either. But still, it's better than fossil fuels, where we certainly release a lot of carbon dioxide into the atmosphere. Okay, was this clear, more or less? Yes? Great. If you have questions, just feel free to speak. Okay, now what goes into a biogas plant? Many things we have already mentioned. Maybe you can try to remember them. Maybe you find some other substrates which we didn't mention so far.
Maybe organic waste from restaurants or something
Yeah.
like that.
Food residues sounds fine. Yes.
The sludge of the water treatment plants.
Yes, that's also right.
The waste of the farm animals.
Yes, that's also right.
I don't know the name. Sorry.
Yeah, we could actually differentiate here between residues from livestock and residues from agriculture. Also, both fine. Anything else?
Agroindustrial waste.
What waste?
Sorry. Agroindustrial waste.
Industrial waste, yes, also correct. Something else? No idea. Anyone there has an idea? No? You maybe? No?
Yeah, it's just that he mentioned one, but it's kind of gruesome. The residue from slaughterhouses, like the blood,
Yes?
the blood, the meat, all of that.
Yeah, that's right.
Yeah.
Okay, I think you have many already. I don't know, did anyone say bio-waste? Bio-waste that we produce daily could also go into biogas plant. Yeah, I think you got many. So leftover food, did you say? Meat scraps, you said meat scraps. Then bio-waste, I mentioned bio-waste. Industrial waste, I think you mentioned industrial waste. Sewage sludge was also mentioned. Then manure, I also mentioned manure. And leftovers from the agriculture. Well, and of course, feces, all kind of feces. Well, this is basically the main groups those are the main groups that we can use to feed our biogas plants. And now a more tricky question: what could we actually do with our biogas plant? So, I mean, we know already that we can produce biogas, but anything else? The biogas production? What would you do with a biogas plant?
Sorry. Maybe because with the biogas, transfer to electricity.
Yes.
In some parts in the world,
Yeah.
and they use this kind of technology to produce biogas to eat, to cooking, to
Yeah, that's
to do
also
that.
right. Yeah, we can use it for cooking. Yeah. For heating as well. Pardon?
As fuel as well?
Yeah, that's also right. We can use it as gas for gas-driven cars. Anything else?
Sorry, man. It's only about biogas or about all the process of the anaerobic?
All the digester.
Oh, maybe for produce biofertilizants?
Yes, that's right. Fertilizer. So now we have electricity, heat, fertilizer, and gas for cooking, and a fuel for cars.
And the treatment of the garbage, the residues, to get
rid of them, yeah.
Yeah.
That's also right, yeah. Yes.
And water, you can reuse the water that you extract for the anaerobic digestion.
Yeah, you mean in water treatment plants that you recover some water. That's right. Yeah, that's also right. Okay, I think we got many. Oh, you have something more? No.
In the water, it's like the sludge treatment.
Yeah.
It's like that. It's like an option to the sludge treatment.
I don't get you.
Yeah, it's like, for example, you have a process, no? You can get the sludge, lodo, si lo estoy diciendo bien, ¿no? The sludge of the process, you can use it in the anaerobic digestion, no?
Yeah, that's right.
It's an option to
reduce the waste.
the sludge.
Yeah, I mean, you said already to reduce the waste. So this goes into the same direction, but you could also mention it separately for the sludge. Maybe not everyone counts it to the normal waste. Okay, here are all the scenarios that I came up with. So remediation of organic waste, you mentioned this. Cooking, heating, power generation, fertilizer, accumulation of valuable metabolites. That's something which is maybe in process. We are not there yet, but people try already to extract fibers. So if you have the digestate, you can separate the liquids from the solids, and in the solids you still have a lot of fibers that you can use to produce, for example, construction materials. We can also use the heat directly at a fish farm which is connected to the digester to heat up the water. We can also use the CO2 because usually we just incinerate the biogas, but then we have a high concentration of CO2 and it's difficult to get gases with very high concentration, very pure gases of CO2, and you could use them, for example, in greenhouses to better grow plants. You also mentioned biofuels. And then, of course, we can add the research that we want to understand how microbiomes are functioning to just better understand this microbial level. Okay, nice. You got most of the options. So, as I told you in the very beginning, we can differentiate between monofermentation and co-fermentation. And apparently, it's problematic to just perform monofermentation. And I wonder whether you have any idea why is that? Why is it not so efficient to just perform monofermentation? What problems are we encounter here? I mean, imagine you have the biogas filled with sewage sludge and now you feed in some glycerol. Does it matter whether you're just putting in some glycerol or additionally some bio-waste? Yes, please.
Maybe if you have only one substrate, you could have a lack of some for a special nutrient.
Yeah, that's
maybe
right.
You can
absolutely
need
right.
to add it.
A disbalance of nutrients. Perfect. Anything else? Any other ideas? You want to say something?
Maybe because of the the bacteria, they could die or not reproduce.
Yeah. Why should they die?
Because they don't have enough reactions. Or
why should they not have enough reactions?
I don't know.
Okay. But it goes into the right direction, so you can have actually problems in the diversity. The more complex the material is that you're throwing in, the more complex is also your microbiome. So you can increase diversity, and we learned already that with more diversity, the microbiomes are more robust. We have a higher metabolic diversity, which also reflects on the efficiency of the biogas plant. So diversity is an important point. Anything else? You have something to say?
Maybe because the substrate is not easily degraded.
Yeah. That's also a good point, yeah. So imagine that you have a substrate which degrades really slow. This could mean that also the microorganisms are not really active. But then if you have it mixed with another substrate which is really easy accessible, then they are continuously eating, they are really active, and in parallel they can also digest the fraction which is not that well digestible. So this is also a really good point. So something else? Yes, please.
The amount of substrate that you can put into the biogas reactor, like if you can only put one type of substrate, there wouldn't be like the amount wouldn't be enough to produce like a significant amount of methane.
Well, let's imagine that we have a lot of this material and that we can throw in a lot of it, that we are not limited in the amount from this one substrate that we are using. So if we have a lack of biomass, then probably no biogas plant would be produced. I know one case like this in a landfill close to Cottbus, and they have a composting system. And I was asking them why not throwing your material into the biogas plant, and they said, well, we don't have enough material to fully support a biogas plant. So in this case, they just don't build a biogas plant. So, well, we could count this as a reason, yeah. Why not? Anything else? Further ideas? No? You have something? Yes, please.
Maybe we have a codification. We can be a better pH control.
pH control, yeah, this could be an important point. Yeah, we could have a acidification which is too fast, and then the pH drops, and then all the methanogens die. Usually the methanogenic archaea are extremely sensitive to pH, so this is also a really good point. Other ideas? Okay, then we will just go through it, and you named already a lot of it. There are a few things missing. So there's a trend towards instability, accumulation of heavy metals could happen. It could happen that a substrate is not available over all the year. So that we have maybe in summer we have a lot of green waste, and then in winter we don't have anything to feed in the biogas plant anymore. Maybe this goes into the direction what you said. Then, yeah, sometimes the methane ratio is also affected, that we just have a very low quality of biogas. We could have a rapid accumulation of organic acids. That's what you said in regard to the pH controlment. And this is important enrichment of nitrogen or ammonia. So this can become really easily toxic. So if you have too much ammonia, then the microorganisms will die or will become really slow, then it's also quite problematic. It could also happen that you have a disbalance which yields to more production of hydrogen sulfide. And this is always a problem because it's extremely corrosive and could damage your CHP plant, where you're incinerating the biogas eventually. And well, you could solve this still with an desulfurization plant. There are systems to cope with this problem. Well, the solution is easy. We just have to use co-ferments, that we always use several substrates in order to circumvent these problems. Sometimes this is not possible. So if you still want to do mono fermentation, you can do so. And here are some strategies how to overcome these problems. So for example, you could regulate the pH with some pH controlling agents. You could also just perform an irregular feeding. So then you take into account, or you just accept that there is not much electricity production in winter and you only use your biogas plant in summer. You could adjust the retention time. So for example, if a substrate is not so well degradable, you have to incubate it longer. This means that you're producing in per time not so much biogas, but still you could efficiently degrade your substrate. You could apply two-stage systems. We will come back to these two-stage systems. It's basically a controlled production of acids with a very high concentration of biomass, and then the acid is fed on demand into the methanogenic stage to produce methane out of it. So I plan to discuss this system in more detail later. We could also apply biochar. It's a supplement that is already used in the industry, and there are some companies who sell the biochar to biogas plants, and they throw it into the biogas plant, and then some substances can absorb to the biochar. For example, ammonia can absorb. It was also found that biochar increases the overall stability of the microbiome, so the microbiome can become more efficient, more robust against disturbances. And we could also add some microorganisms. For example, if we had an acid shock and our reactor died, we could try to add some microorganisms from elsewhere to recover the system. So why is co-fermentation now so beneficial? I will just resolve it. So we basically discussed it already. We have a balanced nutrient ratio. That's what you mentioned before. We have a higher microbial diversity. That's what I think you were mentioning. We have a better buffer capacity. We can also dilute inhibitory substances. For example, if we feed a lot of chicken manure is usually quite enriched in ammonia and nitric substances. And usually it's very difficult to make a monofermentation with chicken manure. But then if you have some part chicken manure and some corn silage and some manure, then you already can reduce the inhibitory effect of the ammonia. We can decrease our antibiotic-resistant microorganisms, which is also nice. We can reach a better quality for the digestate because we have a better distribution of minerals. The nutrient availability can be increased because of better mineralization. And sometimes people also try to produce biochar from the residues from the biogas plant, and here you could also achieve a better quality for the biochar that you're producing from the digestate. Yeah, to highlight this problem, people induced the so-called co-digestion performance index, just called CPI. If the CPI is below 1, it means there's a problem. It means it's not useful to combine the substrates which you are combining. If it's just 1, then there is no effect. Then you could also go for a monofermentation. But very often you have a CPI higher than 1, which means there's a synergistic effect which you could use to increase the efficiency of your biogas plant. And I just looked for one example here, also from Kaki et al. He found a CPI value of 1.9, so he could basically double the efficiency by combining pork manure with corn stover and cucumber residues. So this is much better than digest each of them on their own. Yeah, when we're talking about different co-substrates, we mentioned already that not all of them are degraded very well. And here's just a simple overview on what substrates are usually suited well for biogas experiments or biogas plants. So usually it's really good to have simple sugars, short carbohydrates, amino acids, so things that can be accessed very easily by the involved microorganisms. Then we have fat and oil. It's classified as moderate. Why is that? What problems do we have with fat? Yeah, you have an idea?
Maybe it could be for the gradient of um, of, of the substrate. Wait a minute.
Okay, think about it. We're not in a hurry. In the meantime, maybe someone else has an idea. You have an idea, yes?
Well, if I remember correctly, they're more difficult to degrade because their chains are longer, aren't they? Like they're more.
Yeah.
Also, no, por ejemplo, el jabón. ¿Cómo se dice saponification? Also, you can have saponification, I think.
We don't have what?
Saponification. I don't know if that's the word. I don't know if I'm.
What do you mean by this?
Oh. Like you can, yeah. You can produce soap.
You can produce soap. Well.
And that's not ideal for bacteria.
Well, I haven't heard about this, but maybe it goes into the right direction because we have a problem in the chemical behavior of fat. The problem is it's just not dissolving in water. So it could happen that your fat is just swimming on top of your sludge and then you won't degrade it, of course. It's also right that the molecules are sometimes too long. There's a process called beta oxidation, and this process is quite disturbed without oxygen. It does not work so well then. But usually fat is a quite good substrate in regard to the amount of biogas that we can produce from it. So if we just compare it in respect to the weight to other substrates, you have a really high yield of biogas and methane. This is because the ratio of oxygen to hydrogen is quite favorable. So you have very little oxygen, but a lot of hydrogen. So this means you have less carbon dioxide. All the oxygen goes into carbon dioxide. And you have more hydrogen that you can put on your carbon atoms to produce methane. Therefore, from the yield, fat is really nice, but it's really difficult to make it accessible for the microorganisms because of this problem with the beta oxidation and because it's not so nice soluble in water. Well, and then we have the substrates which are degraded really badly. We discussed them already before, like lignin especially. Here's a picture of one possible formula of lignin, which is just too complex to be degraded efficiently. Okay, those are our basics for biogas production, and I will summarize this shortly. So we have very shortly and simple discussed the functionality of a biogas plant. We also discussed the composition of biogas and its ecological behavior, its ecological relevance. We compared monofermentation versus co-fermentation, and we introduced this co-fermentation performance index. And finally, we discussed the degradability of different classes of substrates and differentiated between substrates which are easy, accessible, which are are in a medium scale, and substrates which are really bad to degrade. Yeah, you can actually pretty easy calculate the amount of biogas that you are expecting from your substrates. And this is demonstrated very easily based on sugar, based on glucose. So you can basically count the C atoms, and you know that each C atom ends up either in carbon dioxide or in methane. Well, then you can count the 2 oxygen atoms. This means with 6 oxygen atoms, you can produce 3 CO2. And then the remaining hydrogen goes on the remaining 3 carbon atoms, resulting in 3 methane molecules. Yeah, and this also has been brought into an empirical calculation, which you can use to estimate the amount of biogas which is to be expected. So you have all the atoms that you find in your molecules. Then you have a counter for how often these atoms occurring. And these counters are then used in this formula to calculate how much hydrogen is needed in order to ferment your substrate. And it also gives you the information how much carbon dioxide is to be expected, methane, ammonia, and hydrogen sulfide. So now imagine that you have whatever substrate you want to use. Imagine you have the formula. Do you think the outcome is always right? Would you say that the result from this formula is always valid?
No.
Yes?
I'm guessing no, because our efficiency will have to be 100% for
That's
it
right.
to be correct.
That's right. So if we calculate this for lignin, we would reach a lot of biogas, but then if we throw it into a biogas plant, we would produce almost nothing. So this needs to be taken into account, of course. So it's like a maximum value that could be reachable if we manage to digest all of it. Okay, now we will come back, or shortly come back to biology, and we will discuss how biogas is actually produced on a biological level. I included here this picture of a cow. This has several reasons. So usually we use manure from cows to fill biogas plants before we start the biogas plant. But this is not the only reason. Another reason is that inside the cow, basically the same processes are happening as in a biogas plant. That's why the manure is so nice to start up a biogas plant, of course. And we are differentiating here 4 phases: the hydrolysis, acetogenesis, and methanogenesis. Have you heard of them before, or is this completely new? You know it, but you're working on it on the field. The other ones? You're shaking your head. So the other ones are not sure? Yes or no? Yes, you know it? So it's okay, so it's not entirely new. Yeah, I will explain it very shortly. So hydrolysis is actually, I mean, you know the term hydrolysis, it's a chemical term. So we try to solve substrates in water to make them accessible. This can also be supported enzymatically. It's like if you imagine that the cow is chewing a certain substrate, it gets smaller and smaller, and then the small particles are getting hydrolyzed. So you try to get it all into a watery phase. And actually something like this is happening on the microbial level in a biogas plant. And we can also support this physically. We can have machines, and they are sold already on the market, which are disrupting the solids in order to make them easier accessible for example, the so-called extruder. So there are like two moving parts which are shredding the wood or the fibers in small pieces so that they're easy accessible. And the extruder or the people who are selling the extruder, they also highlight that they can make wood accessible just because of this harsh physical treatment. Okay, now we have it accessible for microorganisms and they start to ferment. This is something which we call acidogenesis because, as the name says, acid, there are a lot of acids which are produced. So we also produce some gases like hydrogen, carbon dioxide, and hydrogen sulfide. But we are also producing some alcohols and many different organic acids like acetic acid, propionic acid, butyric acid, caproic acid, valeric acid. So there's a wide range of acids that we're actually enriching in the whole process. Well, in the next step, we have a degradation of these acids. They are getting shorter and shorter until in the end, acetic acid is left and as well hydrogen and carbon dioxide. Well, this process actually occurs very often syntrophic. Has any one of you heard of the term syntrophy? You're shaking, no, you're nodding. Yeah, what does it mean?
Syntrophic means that all microorganisms are working together. I mean, one produces something that the other needs. And yeah, that's all.
Okay, then how is it different from a symbiosis?
I don't know how to explain it.
Yeah. Okay, you can think a moment.
Okay.
Maybe the other ones have an idea. What's the difference between syntrophy and symbiosis?
It could be the diversity of substrate.
No.
Okay.
Yes?
Maybe in the symbiosis, each organism or microorganisms don't need the other one. Yeah, they can live together, but only in harmony.
Yeah.
But they don't need it to live. It's like maybe the first one. It's independent. It's not. It's like.
It's not what?
It's independent of the other one. It's like
dependent. Yeah, that's the right word. Yeah, that's right. So yeah, that's correct. So in a symbiosis, they can just work together. They can take profit of each other, but they don't have to. And in a syntrophy, they really depend on each other, and it can be that they are dying without each other. So it's a metabolic interdependence. So maybe it could look like this, but this could also be in symbiosis. But it comes to syntrophy, for example, if we think about these nanowires that we have seen already before. Those are usually produced in order to create a syntrophic relation between the microorganisms. And later on, we will discuss this in more detail. We have another lecture where this is detailed a lot. Okay, and then we have the last step, the methanogenesis, where we are producing the methane and the carbon dioxide now. Okay, here's a scheme which now looks a bit more scientific. Here you have all 4 phases again. We start with the biomass, then we have fermenting bacteria, which are producing acetate, hydrogen, and carbon dioxide, but as well propionate and butyrate and other longer fatty acids during the acidogenesis. Then the hydrogen and the carbon dioxide and the acetate as well are already nice substrates for the methanogenic archaea to produce methane out of this. And the longer organic acids are further degraded in the acidogenesis in order to make sure that only acetic acid remains. And during this degradation, also some hydrogen and carbon dioxide is formed. And these are now the main substrates again for our methanogenic archaea. Okay, now we also understand how this is biologically happening. And now we take a look at the technological level. So we will talk about different solutions for reactors. And we will start to differentiate between dry fermentation and liquid fermentation. So we are talking about a dry digester when the water content is between 60 and 85%. And when we are above this 85%, with the water content, I mean, then we are already in a liquid fermentation. And both things have their disadvantages and their advantages. Advantage is that we have a very small volume for the dry fermentation. We just need less space because there's less water present. But the liquid needs more space, but has the advantage that you can use conventional technologies which are well elaborated. So when the first dry fermenters were constructed, that's relatively new. They don't exist for so long time, and a completely new technology had to be provided to make this possible. And in the case of liquid fermentation, we had already some well-working reactor systems, for example, from wastewater treatment that we could apply here. So it was just more convenient to use the liquid fermentation. There's a favorable material and energy exchange. It's really reliable, and the gas can leave the sludge much easier as if there's a really thick matrix. Well, the disadvantages are that, I mentioned it already, that the volume for the liquid fermentation is really large. And there's a larger effort because of this also for solid liquid separation. And then for the dry fermentation, the disadvantages, I mentioned them already. We need very specific equipment in order to make them work. Yeah, later on we will also see some schemes how these reactors look like. So, oh, you wanted to make a picture? Are you done? Are you done? Oh, fine, okay. So, okay, then we have the mesophilic and the thermophilic digestion. So this is about the temperature. We can have a digestion at rather low temperatures, roughly at 37 degrees, or we can also have some higher temperatures up to 65 degrees. Again, we have advantages and disadvantages. So an advantage of mesophilic digestion is a good process control. So it's really easy to keep the system stable, but you also have less process energy requirements because you don't have to heat the reactor so much, of course. If you have a thermophilic reactor, you have a higher decomposition rate. So you just produce more biogas per time, which is nice. Also, you have disinfection because all the pathogens that can grow on us, they are adapted to the same temperature as we. And our temperature is 37 degrees. So usually pathogens are also growing at 37 degrees. And when we now work at 65 degrees, then pathogens just don't have the right temperature. Yeah, we could also recover the heat actually in order to save some of the electricity costs. Well, then we have some disadvantages. In the mesophilic one, we don't have the disinfection for sure. So the pathogens can thrive. This is actually not the case in agricultural plants. Usually if we have fiber-rich material, there are not so many pathogens growing. But if you think about sewage sludge treatment, then 37 degrees is the perfect temperature to make microorganisms thrive under these conditions. And then under thermophilic conditions, the disadvantage is that they're extremely sensitive. So when there are any fluctuations in temperature or pH in any kind of chemical parameters, then the reactor is easily disbalanced and can go into acidosis, so it basically dies. And also the quality of biogas can be affected when so fluctuations take place. It's also not so easy to start up such a thermophilic reactor. So usually if you start at 65 degrees, it will be really inefficient. So it is recommended to start at 37 degrees, and then you increase it daily for a small amount of temperature until you reach after several weeks or months the 35 degrees. So it takes quite some time to make it work at thermophilic conditions. So then we have single stage and multi-stage reactors. So in regard to the properties, I think it's already said in the name. We have only one stage in the single stage reactor, and then in the multi-stage reactor we have actually many reactors that we are combining. So the disadvantage is it's just really simple with a single stage. But with multi-stage, you can reach higher process stability. Yeah, it's also less affected by certain selection parameters. So for example, if you think about acidosis, when you have a disbalanced process, a lot of acid will accumulate, which will eventually kill your reactor. And this can be prevented in a multi-stage process. So you can produce all the acid in a dark fermentation-like manner in a first stage. And then you're feeding all the acids on demand in the second reactor where you have methanogenesis. So you're basically feeding all the acids on demand. So you don't have an uncontrolled release of acids, and therefore the reactor is much more stable. Yeah, and in return, in a single stage, it's much easier to go into acidosis. Once you've fed too much material, you can't stop acidosis like this. So acid will be produced and the reactor will be disturbed. And the disadvantage for multi-stage is, of course, that you have a higher technological effort, and you can also have some losses in the amount of biogas, because there could already be some biogas produced in the first stage, which you are then not collecting in your methane stage. But of course, you could also think about combining the gas flows so that you're bringing the gas from the first stage, from the hydrolysis stage, then into the methane stage, that all the gas is collected together. Okay, so now we have the basic information how to cluster these kinds of digestion. But there is more. Here's a tree that shows different approaches of anaerobic digestion. As mentioned before, we can distinguish between wet fermentation and dry fermentation. We can do this now at different temperatures or also with multiple stages. So we can combine this theoretically with all the tables that we have just seen. But then we can cluster the wet fermentation and the dry fermentation further. For example, in the wet fermentation, we can distinguish between a discontinuous process and a continuous process. I suppose as engineers you have heard of this before. It's maybe not that new. And a discontinuous process is usually called a batch process or a storage method. What does this mean? Do you know what a batch process is? Have you heard about this before? You are nodding.
Like you treat certain volume at a time, so you put in a reactor sometime, and
Yes.
then you take it out and put another one.
That's right.
New.
That's right. Well, the opposite is now this continuous thing, where we actually feed the material continuously into the reactor, and it leaves the reactor continuously. And then there's an intermediate solution, which we call fed batch. Maybe you have heard about fed batch before. It means that we are feeding continuously in our reactor, but we are not releasing the material. So the reactor is getting more and more filled, and then at some point we just stop feeding, and once it is done, we release all of it, or most of it, and then we start the fed batch again. Yeah, then we have the dry fermentation, which we can also cluster in discontinuous processes and continuous processes. Discontinuous, for example, if we have a fixed bed method, or continuous with the flow-through process. We will see the respective reactors in a moment. We will start with the first ones, with a wet fermentation. And yeah, here we have the batch concept. So you have the reactor, the biogas reactor. You have some input. Then the volume is increasing and increasing until we reach the maximum filling, the maximal filling. And then once this is reached, we pump all out of the reactor, and then we start again. We leave a little bit inside in order to inoculate the whole process, to have some microbiota that can work here. So this is now a flow-through plant, because if you're feeding continuously and you're releasing continuously, you have to leave your material somewhere. And like this, you have a second storage, which we also call the digestate storage. So this process exists, but it's much nicer if you actually try to combine it with some gas collection in the digestate storage as well. So this is a system which we now usually find in Germany, or many systems work like this, that you have your biogas reactor, then you feed it continuously, your material goes into the digestate storage, and here the digestate is kept without much controlling. It does not contain so much substrate anymore, but therefore you're not heating it, you're not steering it, you just leave it as it is, and there is some residual gas produced that you are still collecting, and then you're collecting it together with the biogas from the main reactor in order to minimize the losses in biogas. Usually these systems works like a continuous steered tank reactor, and this is a really simple system. You basically have a vessel with a steerer inside, and then you're continuously steering your material inside these reactors. So to make it a bit more accurate, one could draw in here the steerers as well. So this is a rather unusual system. You have a small mixer, but you're also pumping the sludge from the lower part to the upper part. So where would you expect such a system? Where would you apply such a system? With which substrates? What substrates would you put into such a reactor?
Manures?
Why?
Because it said it's only suitable to very low dry matter.
To very slow what?
Oh. No, sorry.
Okay.
I'm wrong.
Yeah, I would probably apply to sewage sludge. because if you want to mix your reactor based on a circulating pump, this is quite some effort in a normal biogas plant, because in a co-fermenter, in an agricultural biogas plant, you have very high solids, let's say 10, 12%, and it's quite some effort to pump them. So usually you have a big steering system. There are also some pumps because you have to transport your sludge, but it's less convenient to circulate sludge by pumping. This would cost quite some energy. We also have such systems. They are not really common. I guess they were rather experimental. I've never seen such a system in the industry, at least. But, well, apparently they have been applied. And it's a foil reactor. So you have a foil, and then you have a filling mechanism where you put in your substrate with a wheel loader. You're filling the whole foil. You're putting the whole foil onto a heated floor. And in the end, you're connecting some gas pipes where the gas could be released. Yeah, I could imagine it's just too much effort. I don't know how stable this foil is. If you always fill it and remove it again, then maybe the foil also gets destroyed easily. And if you just place it on these heating plates, maybe you have heat losses. So I don't know, to me it looks not so efficient, and I have to see, I have never seen such a system in the industry in Germany, so I could imagine that they were only tried, or that people only tried this on an industrial scale, but it's not really dominating the biogas landscape in Germany. Here's another reactor for solid fermentation in a heap system. So it's a bit similar to a composting system. You have here this heap, and usually you close it to keep it anaerobic. But sometimes you have to open it in order to put in some substrate. So you would put in your substrate here, and you would remove your residual digestate here, and this would result in some oxygen inflow. This means the input is quite oxic, and the layer behind the input also gets enriched with oxygen, so it's also aerobic, and then it becomes facultative. So the further away you are from this filling part, the more anaerobic you are. Here you have a long fraction of anaerobic sludge or anaerobic manure, which is then producing a lot of biogas. So after this filling procedure, you close it, you ferment for a while, then you open it again, and then you put another amount of substrate, another pile of substrate here, so you attach it to this part, and you remove this part which was previously here, and then you repeat this again, so that actually this filling gap is wandering into this direction, and once you're ending here, then you can restart here. Is this clear, more or less? Yes? Okay. So if you have questions, feel free to ask. Just checking the time. Okay, we have half an hour left. So this is now, this system, I haven't seen this either, I have to say. So I could imagine that there were some industrial experiments with this, but this is also not a typical kind of biogas plant that I have seen in the industry. And in regard to the dry fermentation, a system which is used very often is this garage system. We really call it garage because you can drive in with a car and they are actually doing it. So they take the wheel loader and then they're piling up the biomass inside. Afterwards, they're closing this garage and then it starts to produce biogas. To achieve this, they have actually a liquid phase, which they're sucking up from below, and then they're pumping it into into the top, and from there it's trickled over the solid bed, over the pile of biomass, in order to always have some liquid film on the pile of your biomass. Well, and once you're done, you empty it out again, and then you can fill in the next pile of biomass. This works, but this system has a problem, because usually, since you have so much substrate in it, it's possible that you're accumulating the organic acids too fast. So with the organic acids, you will inhibit the methanogenic archaea, which are extremely sensitive to pH. So it could be that for a long time, nothing happens. And then after quite some waiting, methanogens will adapt, and eventually they will again produce methane. But it will take quite some time, and you can circumvent this problem. I come later to this here. I wanted to highlight that it's not recommended to smoke in these plants. And yeah, there are really accidents that happened already. So if such a plant catches fire, this can be huge. So no smoking close to a biogas plant. So, but now we come to the thing that I actually wanted to say. So if you have too much acid produced, then then the methanogens, they just won't work, and it will take too long. And you can circumvent this problem if you have a liquid fermenter nearby with liquids. And then you're trickling or spraying all the liquids over your pile of substrate after filling. And the acids that are enriched here are then pumped into this liquid reactor. And then you can degrade easily all the volatile fatty acids, and then you have material with less organic acids and higher buffer capacity, which you're pumping again on your pile of substrate. Oh, sorry. Yeah, and then this system is also quite often applied, I would say even more often than this garage system, and this is a plug flow reactor. It's also used with really high concentrations of total solids. And yeah, it works like this, that you have this big reactor, and then there is a really big pedal. So it's turning the substrate in order to move from this side to this side. And then you have some heavy pumps here in order to include the material and to take it out again. So it's rather simple, but due to these large pedals, you are able to move the substrate even with very high concentrations of solids in order to allow digestion of solid materials in such an reactor. You can also combine all these reactor types. For example, here you have a pre-pit where you collect some manure, and then you bring it into a wet fermenter where it's digested, and then you have your digestate, which goes in a post-digester, and from the post-digester in the digestate storage. This is an interesting concept which we didn't discuss so far. We had this multi-stage concept where you have this acidification stage followed by a methane stage, but sometimes people are also coupling two methane stages in order to degrade the substrate just more complete. So in this case, we have actually two methane stages after another. And from the post-digester, where the acids are degraded relatively well, you send the liquids into a dry fermenter, where we usually have a problem of enriching too many acids too fast, and we can buffer them with a well-degraded material from this post-digester. And well, then the solids from the post-digester go into a digestate storage, and in the end you end up with some fertilizer. Also from the dry fermenters you get some fertilizer. In all these reactors you are producing gas, of course, which can then be incinerated in the CHP plant. CHP, I mentioned already several times. Do you know what CHP means? So it stands for Combined Heat Power Plant. So basically you incinerate your biogas, and then you have maybe 45% of electricity and 55% of heat that you have to use somehow. If you're lucky, you have a heat grid nearby, and then you can use the heat to distribute it to different households. Yeah, here's an concept how it could look less schematic in a more industrial scale. Don't worry that the words are so small. I will enlarge them now step by step. So we will start with the corn silage. So we need a storage for all our silage, and then we are transporting this silage into a feeding unit, from where we are feeding it into our first digester. We also need some liquid manure, otherwise we couldn't have a liquid fermentation, which we get from our cows. And then we have a second digester. So it's similar to the scheme that I just showed you before. We want this post-digester in order to be sure that we are degrading really everything, because sometimes you have the problem of shortcuts. So it could be that you're feeding in some fresh material, and then due to mixing, it could happen that your fresh material relatively fast leaves the reactor again, and then you're not degrading it so efficiently. And this can be circumvented, this problem, if you have a second digester, and then it's kind of redigested, and then you make sure that you really digest all the material that is going into the reactor as good as possible. Then you have the digested storage. And from there we have the fertilizer. We can take the digestate, we can bring it on the fields as a fertilizer in order to grow our corn again. And yeah, here's a cornfield, and actually this is the case in Germany, that most of the agricultural biogas plants are fed with corn. Yeah, why do we do this? Why do we always use corn for biogas plants? Maybe you can solve this question if you think about our photosynthesis lecture.
Because it have a lot of starch.
Yeah, I would accept this question, but I wanted to hear something else.
Could be for the rapid growth cycle.
Yes, and why is it so rapid?
For the growth cycle.
Yes. Why is it so fast?
Because it's a C4 plant.
Yes, exactly. It's a C4 plant. That's right. Yeah, people are discussing whether it's useful to grow so much corn for biogas plants when we should eat it. But you could also just feed in the green part of the plant and then use the corn as fodder for the animals, or eat it yourself. Well, so now we have produced a lot of biogas, and usually this biogas contains quite some sulfur. And I told you that the sulfur is quite corrosive, so we have to get rid of it. And for this we have desulfurization plants. There are special kinds of microorganisms. They need some oxygen, so you feed them with some oxygen, and then they're able to degrade the hydrogen sulfide in order to get a biogas which is more pure. And then you can even filter it with carbon, for example, and then you have a biogas which will probably or hopefully not damage your CH4 plant. Sometimes if you're producing too little or the quality is really bad, you can also send it to a flare just to get rid of it. But the best way, of course, is to send it to your CHP plant, where you can incinerate it now to produce electricity.
Sorry. I have a question about the
Yes.
past slide. What is the function for the corn silage?
For the silage?
Silage, yes.
Yeah, that's a good question. So the corn, when does the corn grow? So there are only certain growth periods in, in Germany we have the problem of the winter. In winter we can't grow any biomass. So we have to store the biomass somehow. But if you just store it somewhere piled up, then it will degrade. It will be there rotten, not usable anymore. In order to prevent this, we have this silaging process. And then the lactic acid will conserve the biomass for ages. And then you can step by step take it and feed it during the winter.
Okay, thanks.
Welcome. Okay, any further questions? All clear? Okay, great. Well, that's all that we are hearing about the technical approaches. Again, I will summarize this shortly for you. So we have here now this 4-phase model with the hydrolysis, acetogenesis, and methanogenesis. We also heard about calculation of biogas yields, which are, of course, not to be fully trusted because not all substrates are fully degradable. We have to take this into account. We have differentiated between wet and dry fermentation. Also, we highlighted the influence of different temperatures, mesophilic and thermophilic temperatures. We saw a possibility tree for technological approaches that we can follow to build up our biogas plants. And we also saw some fermenter concepts, how we could actually use them in a practical scenario. Well, now we come to the next topic, which is the dark fermentation. I don't know, do we have enough time left? 15 minutes, yeah, we can start. So we'll get at least an idea. And I will present this based on this article, which is really nice, I would say. It's a review article where they try to give a kind of holistic view on dark fermentation. So now I will ask again the question, what makes dark fermentation so different from a methane stage? So we learned already that there is methane production that we want to prevent, and that we just want to follow, well, the first phases of the anaerobic digestion processes in order to have this dark fermentation. So how do we stop the methanogenesis now? Maybe you got an idea in the last slides. We talked about certain stressors for biogas plants. We could apply them. So what would you say? Do you have some idea? The answer will come, but maybe you have already a creative idea.
Maybe you have like a reactor to catch all the hydrogen before it reaction with the CO2.
Yeah. But what happens if in the reactor where you're producing the hydrogen, what happens if there are methanogens growing? And when they're eating the hydrogen before it's actually released into the gas phase? This happens actually quite often. So the hydrogen releasing bacteria, they live extremely close to the methanogenic archaea. And then the archaea take up the hydrogen as it is released from the bacteria. So how can we solve this? Okay, so I will present you some solutions. So we have now many slides which are discussing this topic on how to inhibit methanogenesis. So why should we do this? Here's a scheme, a really holistic scheme on all the products that we can produce. So we have our anaerobic digester in the center, and we can produce some biogas, which is the current status. and we get some biofuel, electricity, and biofertilizer. So this is where we are now. And we would like to move into this part of the scheme where we get some hydrogen and, more important, the volatile fatty acids. And with this, we could produce biofuels, bulk chemicals, bioplastics, nutrient removal from wastewater. Okay, this could also be here, and food additives. So I think that this part is important, the bulk chemicals and the bioplastics. That's something new that we can achieve. And the hydrogen, well, there are hundreds and thousands of articles talking about hydrogen production in dark fermenters, but still it's not coming into the industry. So people are arguing whether this is economically feasible or not. We know how to do it, we know how to collect the hydrogen, but apparently it's so little that the industry has not enough interest in this, at least not yet. But the volatile fatty acids, they could be quite interesting and could yield much more money in the end than just selling the methane. And here's a nice table on all the products that could be produced from the volatile fatty acids. So the idea is that we have our waste, we produce our volatile fatty acids, we provide them to the industry, to the chemical industry, and then the chemical industry can produce a wide range of products with this. For example, from acetic acid, we can produce food additives, plasticizers, and dyes. Or from propionic acid, we could produce resins, pharmaceuticals, and paints. From butyric acid, we can produce pesticides, food additives, and paints. This was isobutyric, sorry. Here are the butyric acids. We can produce pharmaceuticals, perfumes, and fungicides. Then we have the isovaleric acid. From the isovaleric acid, we can produce, I think I was jumping the line before. So we are now with the pharmaceuticals, perfumes, and fungicides, and we had the perfumes, textiles, vanishes, and plastics for the butyric acid. Well, we have the valeric acid with perfumes, plasticizers, and lubricants, and the caprylic acid with rubber, grease, and tobacco flavor. So I think this is huge. There's a wide range of products that we can produce that we need and which are definitely more important or more expensive than methane. So how to produce these organic acids? We can do it in pure culture. There are actually many organisms that have been described in the literature to produce these kind of organic acids. Just to give you here some example, all these are organisms that are producing acetic acid. I'm not going to read them. You don't have to remember them either. It's just to get some visual examples. Here are some examples of organisms that are able to produce lactic acid. So if you're making a pure fermentation with just one of these organisms, you will get lactic acid. Or we could use these organisms to produce propionic acid in pure culture. Here we have some organisms that we can use for hydrogen production. And there are even organisms for thermophilic hydrogen production. So those are just examples, and I would say the list that I'm giving you here is just the tip of the iceberg. So we have countless organisms that we could use to produce all these organic acids, which are so valuable. There's just one problem. We don't want to work with pure cultures because it's really expensive to work with pure cultures. We want to work with mixed cultures. They are much more cheap, and we don't have any problems with contaminations. So if you have a really large batch and it gets contaminated, you can throw it all away, but this will unlikely happen in a mixed culture. But in the mixed culture, we have the problem that we can't really control the outcome. How can we control that there is just acetic acid produced or just butyric acid produced, or at least that we produce acids and no methane. Well, for this we should take a look at the different phases of anaerobic digestion, starting with the hydrolysis, where we are disassembling all our molecules to make them accessible and easier digestible. Then we have our second phase, the acetogenesis, where we are producing all the organic acids, maybe also acetogenesis when we want to produce acetate. So these two phases for the acid production. And then we want to stop methanogenesis in order to stay here to make sure that all the organic acids are not further degraded. And this brings us now to the next point. I don't know whether we still have time. We have 5 minutes. Yeah, we can talk a little bit further. So we can inhibit methanogens with pH. So there are different studies on how to manipulate actually the acid production based on the pH. For example, if you are using a very high pH, then you will get more acetic acid. If you're using a lower pH, then you get more butyric acid. In order to achieve this, you have to control your pH, because during the fermentation, the pH will change continuously. So you need some kind of pH control system. And this pH is also really nice to inhibit the methanogens. So they're extremely sensitive to pH. And usually with a pH below 6, they're already quite inhibited and don't produce so much methane anymore. We can also manipulate the whole process based on the organic loading weight. So here are two values. One loading weight with 9 grams of total solids per liter, where we could get a really good yield. You can increase the loading rate, and with this you will actually produce more, but the efficiency gets reduced. And you can imagine that you're eating like this guy, and if you're eating so much, you will just release a lot of material which is not digested very well. So it's the same with a biogas plant. Yeah, we can also talk about temperature. So there are different studies on how to manipulate acid formation, and generally people say that mesophilic temperatures are better. If you have very thermophilic or hyperthermophilic temperatures, you could hydrolyze the material a little bit better, but at some point the solution gets saturated, so that this effect is not so helpful anymore. But I would not fully agree to this statement, because we have seen that thermophilic biogas plants are quite efficient, and I think it's about adaptation. So if you adapt the whole microbiome for months to a very high temperature, then I could imagine that you are also increasing the acid production rate by this. Yeah, we can also work on the hydraulic retention time in order to retain the biomass longer in the reactor to increase the overall yield of acids that we want to produce. But at some point it could also be that it's not so economic anymore, because if we have a really high efficiency, then we retain the material for a very long time without adding new material, so it gets maybe less efficient. And also the chemical equilibrium is really important, because imagine that this is our organic acid that we want to produce, and if it's present in a very high amount, then the chemical back reaction could be favored, so that we are just not producing so much organic acids anymore. So these things can all be used to manipulate the acid formation, and we talked already a little bit about the possibility to also inhibit methanogenesis, and I think that's something that we have to finish tomorrow, because now it's 5. So thank you very much for your attention. See you tomorrow. Are there any questions left? apart from the question how we suppress methanogenesis? Okay, then thank you very much and see you all tomorrow. Bye. I got a message from one who was following online YouTube, and he told me that he couldn't access the data. I don't know why. I don't know, but he will try to gain at least, probably because all of them I have to call